All right, what is up, YouTube and Dr. Hurley? Tonight for my ME 442 final project, I'm going to be conducting the third experiment in the corrosion kit titled the Fruit Juice Objective, in which I use citric acid as the conductor between two metals so that I'm able to analyze the potentials of those metals and the differences between those potentials using copper as the reference electrode. And so then I can draw conclusions about the ability for galvanic corrosion to occur between these metals that I will experiment on. And finally, draw conclusions about the effectiveness of galvanic corrosion between these two metals and the rate at which it will occur and things of that sort. Let's get into it. I'll be starting off with a quick overview of my very fancy and elaborate experimental setup. To start off, we've got my sheet of paper on which I've drawn a table which is ready for data to be input. As you can see, metal number 1, the reference electrode, is copper. Metal number 2 are these 4 metal strips along with the one that's already in the orange. That will be compared to the copper reference electrode. The fruit is orange, and the voltage is to be determined. I've got my voltometer, which is hooked up and ready to be connected to these metals. I've got my test orange along with a couple extras in case this one gets juiced. And I've got my battery hooked up to the metal, which will provide a little flow of electricity within the circuit and allow me to gather some accurate electronic voltage potentials. And you can't forget the most important piece of equipment in any scientific experiment, the safety goggles. These are going to keep my eyes protected from any stray orange juice that may be spraying around the room. It's very important to keep your eyes protected at all times during any experiment. All right, YouTube, are you ready? I'm going to kick off this experiment by first measuring the difference in potentials between the reference electrode, copper, and the first metal that I'll be testing on, which is aluminum. I'm going to measure the difference between their potentials and be able to draw conclusions about how quickly galvanic corrosion would occur when compared to the other metals in this experiment. Let's do it. Step 1 is to connect one of the leads from the voltometer to your reference electrode, like so. Step 2 is to connect the other lead from the voltometer to the metal that you're testing on, like so. And when this happens, you get a reading on the voltometer. This one happens to be 0.5 volts, which I will then record on my notebook. This is what the voltometer reading looks like on my end, just so you guys can get a glimpse. I'll attach the leads to the metal. And as you can see, the difference in potentials is about 0.5 volts. I will now mark this data down on my table and repeat that process with the 4 metals that have yet to be experimentally observed. All right, metal 2 is connected, which is lead in this case. And when connecting the leads, I'm getting a reading of, switch them around, what looks like 0.4. I would say 0.4 more often than 0.3, so that's what I'm gonna go with. Marking it down. Yeah. It's time for 10, baby. Let's see what we got. Looks like 1.8. Holy moly, that is some galvanic corrosion. Marker down. All right, next up is Mr. Zinc. Looks like we got 0.4. Cool. Last but most certainly not least is magnesium, with a reading of 0.8 volts. I'm going to repeat this process a couple more times just to ensure the accuracy of my results. If they don't look accurate to you, Dr. Hurley, it's quite possible that I mixed up the metals when recording my data. In the C-Kit handout, there was a way to distinguish between the metals, but the metal strips in my C-Kit were cut to different dimensions than what the C-Kit handout explained they should be cut to. So I kind of just had to use my best judgment. But I feel like I did all right, and the data that I gathered looks pretty good to me. As for the analysis of the effectiveness of galvanic corrosion between the metals analyzed in this experiment and the rate at which that galvanic corrosion will occur, according to my data, the copper and the tin had the highest difference in potentials. So when these two metals are connected and exposed to the atmosphere, and all four requirements of an electrochemical cell are checked, galvanic corrosion will occur between these metals quite quickly. On the other side of the spectrum, copper and zinc, as well as copper and lead, had a fairly low difference in potentials. And so when copper being the anode and zinc or lead being the cathode in an electrical chemical cell are connected and exposed to the environment, galvanic corrosion will occur, but at a much slower rate than when compared to, say, tin. This experiment also goes to show that you don't necessarily need a typical corrosive environment such as acid rain or salt water to cause corrosion. Any metals that are connected in an electrochemical cell with an electrical charge flowing between them, even when, say, citric acid is the conductive fluid, corrosion is still bound to occur. And thus it's very important to use our best judgment when using two dissimilar metals in a design, because galvanic corrosion is always a threat, even when you think the environment is pretty corrosive resistant. Thank you everybody for watching. I hope you learned something. I hope you got inspired to try this experiment for yourself at home. And I'll end it with one more look at my data. This is what I got. I did 3 trials on each metal combination, and I got pretty similar results on each trial. So I'm assuming these results are fairly accurate. And as you can see, the copper and tin combination has the highest potential for galvanic corrosion, while the copper and zinc, as well as the copper and lead combination, have the lowest potential for galvanic corrosion. However, galvanic corrosion is always a threat, and this can occur when any two dissimilar metals are connected in an electrochemical cell. Thank you so much for watching, and remember to always use safety glasses when doing a scientific experiment. I hope you all have a great night, and